Hello everyone. I'll present my joint work with Broadbent on QMA-hardness of consistency of local density matrices with applications to quantum zero knowledge. As the title says, the main object of our work is the problem of consistency of local density matrices. And intuitively, this problem consists of the following. So we're given m pieces of a quantum state on k, and each piece consists of a density matrix on k qubits, or k here is a constant, let's say 6. And our goal is to understand, so you have to decide if there exists any qubit state that is consistent with each of these pieces. So let me be a bit more formal. So we're given as the input as the 2 to the k by 2 to the k matrix of matrices row 1 up to row m. And our goal is to say to decide if there exists some quantum state psi on n qubits, such that when you look to the reduced density matrix corresponding to some density matrix rho I, it is exponentially close to it. Or if for every psi there exists some I, such that psi on the corresponding qubits of rho I is very far from it. And here very far, okay, so an inverse polynomial gap. And our goal here is trying to understand how hard this problem is. And in order to formalize the hardness of this problem, we will go one step back and review some concepts of complexity theory. And the first concept that we want to remind you is the well-known class NP, which formalizes the notion of deterministic verification. And we say that a problem is an NP if there exists a deterministic algorithm D that receives two inputs: X, an input to the problem that we want to decide if it's a yes instance or a no instance, and a candidate proof Y for X. And given these two inputs, the deterministic algorithm D should accept or reject. And to say that the problem is an NP, we need two properties from this D, is that for positive instances, there exists some Y that makes this algorithm to accept. But for no instances, no matter which Y is provided, this algorithm should reject. We can then extend the notion of NP to the quantum setting, which gives us definition of the complexity class QMA. And we quantize these definitions in two ways. So first, we have that the verification algorithms are now quantum polynomial time algorithms. And the proof that is provided to this quantum verification algorithm is a quantum state. Now, what we want to, the properties that we want from the QMA protocol is that for yes instances, there must exist some quantum state psi that's provided to Q that makes it accept with high probability. And for no instances, no matter which quantum state is provided to Q, Q should reject with high probability. And going back to the consistency of local density matrices problem, what Liu showed in 2006 is that this problem is in QMA, and this is not so hard to see. So the idea is that the prover could provide copies of the state psi as a proof, and the verifier would just check if psi is consistent with a randomly picked rho I. What Liu also showed is that this problem is QMA-hard under Turing reductions, but Turing reductions, as you might know, is not the standard type of reductions that you want for hardness and completeness. And Liu stated as an open problem, trying to show that stated as an open problem if consistency of local density matrices is indeed QMA-hard, but now under CARP reductions, standard CARP reductions. And in our work, our main technical contribution is showing that this problem is indeed QMA-hard under CARP reduction. And we also show some applications to quantum cryptography. And before diving into our technical result, we just quickly explain the applications that we have for quantum zero knowledge. And zero knowledge protocols, they appear in these interactive proof settings, where instead of having just one message from the prover to the verifier, they can both exchange messages back and forth. But now, what the extra property that you want from this protocol, the zero knowledge property, is that the verifier does not learn anything from interacting with the prover. Since we want to be secure against the verifier not learning anything, we might even assume that the verifier might be cheating and not following the protocol in order to learn as much as you can from the protocol, from the prover. And as I said, the goal is to say that even this malicious adversary is not learning anything from that she should not be able to learn by herself. The question is, how can you formalize such a property? And we do this by defining simulators. So by that, we might assume that this malicious verifier, after interacting with the prover, outputs some quantum state row. And to say that this protocol is zero knowledge, we have to define a polynomial time simulator that might depend on V, but it does not depend on P. So it cannot interact with P, nor has any access to its internal structure. And the simulator should output some quantum state sigma. And we say that this protocol is computational zero knowledge if these two quantum states, rho and sigma, they cannot be efficiently distinguished. Or more formally, we say that the protocol is zero knowledge if for any polynomial time, quantum polynomial time distinguisher A or algorithm A should behave the same almost the same if she was given as input the quantum state rho or the quantum state sigma. And there's been a lot of work on trying to provide quantum zero knowledge protocols for QMA. And actually, we know that they exist for quite a long time, because if you know that if quantum one-way functions exist, then using using complexity theoretical inclusions, you can have a zero knowledge protocol between a classical prover and a classical verifier that is also zero knowledge. But the problem with this protocol is that since the prover and the verifier are classical, all the structure of the quantum proof is gone, and the prover must run in exponential time. More recently, in this work of Broadbent, G, Song, and Watrous, they show that we do have quantum zero knowledge protocols for QMA, where now the prover is polynomial time, given that the prover is provided the quantum witness. So the idea here is that a third party gives the prover the quantum witness of the QMA problem, and after that, the prover should run polynomial time. And although they show a protocol with these properties, their protocol is rather complicated, and it has multiple rounds of communication. And it is not as simple as the protocols, the zero knowledge protocols for NP, such as the coloring one that is known as a commit and open zero knowledge protocol. In our work, by using these QMA-hardness of consistent of local density matrices that are based on these locally simulatable codes from the work of Grilo, Zlofster, and UN, we finally can show very simple zero knowledge protocols for QMA. And I'll quickly describe this protocol now. So we show this zero knowledge protocol for QMA by showing a zero knowledge protocol for consistency of local density matrices problem. And since in our work we showed that this problem is QMA-hard, then we finally have a very simple zero knowledge protocol for QMA. So in this protocol, we have that the verifier has the input to the consistency of local density matrix problem. So she has the description of density matrix rho y, rho 1 up to rho m. And the prover is supposed to have copies of the witness. So it's supposed to have copies of the state that's consistent with each rho y. Then this prover P, what he will do is apply a one-time pad encryption on this quantum witness. So it apply random Paulis on the state row to the L. And instead of giving the one-time pad keys to the verifier, it will put them on safes or to do a commitment of these one-time pad keys. And then P will send this encrypted state and the committed strings, but will keep the keys to open each of the safes. The verifier then picks one of the i's from 1 up to m uniformly at random and asks the prover to give her the corresponding keys that will allow her to open the commitments to the one-time pad of the qubits corresponding to her y. Then, when the prover gives back these values of the keys, the verifier can indeed can then open the commitment of these one-time pad keys, undo the one-time pad encryption for the corresponding qubits of the matrix y, and then run the QMA verification that Liu proposed in 2006. I don't have too much time to explain these in details, but it might not be hard to see that this problem is complete, because if the prover and the verifier are honest, then the verifier will get convinced with probability, with a very high probability, and the probability is the same as the probability that Liu protocol, the completeness of Liu's protocol. And the same thing for soundness, because from the point of view of the verifier, she's doing the exact same test that she would be doing in Liu's verification. And the main thing that we need to prove that this protocol is zero knowledge. And intuitively, this protocol is zero knowledge because the only thing that the verifier is looking here, so in particular, the unencrypted density matrix of some rho I, this is already known by her because she has the exact description of the density matrix. So the quantum state that she has access to that is unencrypted is already fully known by her. So let me be a bit more precise. So, and as I said, for proving zero knowledge, you have to do provide simulators. So let's first show our first attempt and show the first simulator that just picks I uniformly at random. And then instead of using the state psi, performs the same protocol, but just putting the symmetries of her y in the right places, and let's say zeros elsewhere. And then run the same protocol as the anonymous prover would do with this malicious verifier. It is not hard to see that since the simulator picks I uniformly at random, it will guess correctly the challenge sent by the verifier with probability roughly 1/n. Because even if the verifier was cheating and not picking a uniformly random I, the simulator would guess with this probability because the simulator is picking at random. And what we can also show is that whenever the simulator succeeds, and by succeeding it guesses correctly the same I that was challenged by the verifier, then the output of the simulator is exactly the same as the output of the malicious verifier. The final step to bootstrap this simulation on these restricted cases where we guess I correctly is by using the rewinding technique of Walters that allow us to amplify the success probability, and when we but still outputting the state that is indistinguishable at the same time. And this finishes my quick explanation about our zero knowledge protocol. And now I'll explain some of the details that allow us to show QMA-hardness of consistency of local density matrices. And our main tool here is using quantum error correcting codes. And I'll explain some properties that we need from error correcting codes by example. So and the example that I'm taking is the Steane code that maps this qubit 0 to this code word here, and the qubit 1 to the second code word here that you can see here. And one interesting property of the Steane code is that imagine that you have an encoding of some quantum state psi that's unknown. And imagine that you want to compute the redundancy matrix on 2 qubits of the 7 qubit codes. And it's not hard to see if you do the tedious calculations that for every quantum state psi that's encoded, or for every qubit psi that's encoded here, and for every positions that you want to calculate this redundancy matrix, the output, the redundancy matrix on these 2 qubits for every psi is just the identity. So this is the totally mixed state. And this can be proven just by inspection. So in particular, that it means that given 2 positions I and j, we can efficiently compute the redundancy matrix of any encoding of a qubit psi with this Steane code. And these algorithms are simple, you just output the identity. But unfortunately, it works for 2, but not for 3, because you can see, for example, if you the encoding of 0 and the encoding of 1 can be distinguished by just looking at the first 3 qubits. Okay. So our idea here is to define what we call simulatable codes. And this is having these properties that we saw for 2 qubits, but now extended for, let's say, s qubits. So what we show is that for any fixed s, if you use this concatenated Steane code, so if you pick a qubit of the Steane code and encode it again using the Steane code and repeat this for k times, then we can we have these new correct encodes like this concatenated Steane code has some very interesting properties. And the first one of these is that there exists an algorithm, a classical algorithm that runs in time polynomial in 2 to the k, and it computes the redundancy matrix of encoding of any quantum state row according to this concatenated Steane code without knowing the encoded state row. And the idea is more or less what we saw before with the one-shot Steane code, but now repeated with s qubits and using this concatenation to prove that that this is independent of the state row, and this can be efficiently computed. And the second property that we have from these concatenated Steane codes is that we not only can compute the redundancy matrices of encoded states, but we can also compute redundancy matrices of computations on concatenated Steane code. And as we saw, as we know, with using techniques from fault-tolerant quantum computation, one can compute unencoded data by 2 forms. So first, using transversal gates. So for instance, with the concatenated Steane codes, if you want to apply a Clifford gate, we can just apply it transversally, meaning applying on each physical qubit independently. But this is not universal for quantum computation, and to do universal quantum computation, we need extra resources. And these extra resources are the T gadgets that receive let's say a T magic state, and then you only do Clifford computation on that. And just to recall, so the second property tells that, for instance, if you want to apply Hadamards on this encoding of the state row, not only we can compute the redundancy matrix on row, but on row after applying Hadamard on each physical qubit. So for every snapshot that you have here, you can compute the redundancy matrix on let's say s qubits of this encoding of the partial computation of Hadamards on the encryption of row, on the encoding of row. Then, this is this is the main tool that we need for proving the QMA hardness of this consistence of local density matrices, and this was defined by in the work of Grilo, Sloft, and Newman. And let us give us the second tool that we need for proving this QMA hardness, and this is the circuit to Hamiltonian construction, and sometimes called the Feynman-Kitaev construction. And these allow us to convert quantum circuits to Hamiltonians. So what Kita showed is that if you were given a quantum circuit V that is decomposed on, let's say, 1 and 2 qubit gates, U1 up to UT, and some initial state psi neat, you can reduce the computation of V on the state psi neat by, we can reduce to a Hamiltonian HV, such that if V accepts with high probability, then we can, the ground energy of this Hamiltonian is low. And in particular, a specific state that has low energy is the history state of the computation. And the history state of the computation is described as a superposition of every snapshot of the computation of U1 up to UT on psi. So more precisely, we have the uniform superposition for every timestamp t from 1 up to t, from 0 up to t. And tensored with this timestamp that you have here, we have the computation psi, and you apply on it U1 up to U little t. A second property of this Hamiltonian is that if this circuit accepts on psi neat with high probability, with low probability, then the ground energy of this Hamiltonian HV is high. So this reduces the acceptance probability. This reduces computing the acceptance probability of V on psi neat to computing the ground energy of this Hamiltonian HV. And our goal here is to tweak this reduction from circuits to Hamiltonians in such a way that when you consider the Hamiltonian of this tweaked circuit, we have a history state that is whose density matrices are efficiently computable by a classical algorithm. And once we have this algorithm that computes them, we have our reduction from any QMA problem to consistence of local density matrices. And here is our tweaked circuit. So instead of running the circuit U1 up to UT in the clear, we consider a modification of V that will apply the computation on the encoding of psi neat and apply the encoded version of U1 up to UT. So here, our QMA verification, instead of receiving psi neat, that they say psi, it will receive the encoding of the one-time pad of psi. And the one-time pad here, it is only for technical reasons, but the main and crucial point here is that this stage is encoded under a simulatable code. Then this new verification V prime, it checks if the encoding of each qubit that was sent by the prover is correctly encoded with the error correct encode. And if this is the case, then the V prime can undo the one-time pad key, and it can do it in the encoded state. Encode auxiliary qubits 0 and T magic states, and then this V prime can apply the verification algorithm V on the encoded states. And once she does that, she could just decode the output qubit and decide to accept or reject. And what we can show is that with this tweaked version of this quantum circuit, we show that if there exists a classical simulator that computes in polynomial time the reduced matrix of the history state of the encoded verifier. And we show that there exists a quantum state that is consistent with these density matrices if and only if this verification V accepts with high probability. The proof of hardness, it follows three main steps. So first, we can show that you can compute any snapshot of the computation in this, any snapshot of this encoded computation. Then we show that you can simulate intervals of the snapshot of this encoded computation. And finally, we can wrap all together and show that the history state is efficiently simulatable. And to finish, I'd like to state some open problems. So first, we have been designing better and better protocols for quantum zero knowledge. And so classically, zero knowledge protocols have a lot of applications, but quantumly, we don't have any clear application for these. So can you find applications for quantum zero knowledge? Secondly, can you study zero knowledge in this strong non-signal setting? Or can you have quantum non-interactive zero knowledge where the verifier and the prover have access only to a common reference string? And finally, something that I didn't mention in my talk, but we can see in the paper, is having more efficient proof of quantum knowledge protocols. And thank you for your attention.